Welcome to Lecture 40, which is our final lecture on electromagnetism, but it's not just a summary. In fact, we're going to introduce a new phenomenon, which is arguably the most important phenomenon in electromagnetism. Now, we're going to have to put a lot of stuff together. We know a lot about electromagnetism. We've seen practical applications of electromagnetism in things like generators and batteries and circuits. We've looked at fundamentals like electric charge and magnetism, magnetic fields and electric fields, and I want to cut through to the basics because the really important things in electromagnetism are the fields. And I hope throughout the course of these lectures, the fields have kind of grown on you in reality. Perhaps the biggest leap into reality was when we understood that the fields carry energy, which we did with capacitors quite a while ago, and we did with inductors back in Lecture 38. So let's look now at the fields and understand what we've done about the fields. Implicit in everything we've said about fields are actually four fundamental and different statements about how electric and magnetic fields behave. So what do we know about electromagnetic fields? We know, first of all, that electric fields arise from charges. Coulomb's law and its geometrically very different but equivalent law, Gauss's law, tell us how electric fields arise from charges, and they tell us in particular that electric field lines begin and end on charges. We also know about magnetic fields and how they arise from moving electric charges, and they arise through the Biot-Savart law and Ampere's law. They describe moving electric charges. Magnetic field lines, we know, don't begin or end. There's no magnetic analog of electric charge. There's no such thing as a magnetic monopole. That's different from electricity, where there are monopoles, electric charges that give rise to electric fields. Finally, we know that changing magnetic fields give rise to electric fields, Faraday's law of electromagnetic induction. So there are four English language statements of what we know about electricity and magnetism, in particular about the electric and magnetic fields. Now, this is not a course in calculus, and you don't need to understand vector calculus to understand this course. But I do want to make the statements of electromagnetism mathematically without understanding all the details, so we can talk about them mathematically and we can understand the big insights that gave us the complete picture of electromagnetism in the 1800s. So I'm going to begin with Gauss's law for electricity, which, remember, is equivalent to Coulomb's law. And all these laws have a form. On the left-hand side, they begin with this funny, sort of distorted S-shaped thing. That's an integral sign, and it means we're adding up a lot of stuff. And in this case, the stuff we're adding up looks sort of like E, electric field, times A, area, little bits of area. That's what the D is doing to us in calculus. So the left-hand side is actually the electric flux, or equivalently the number of electric field lines emerging from a closed surface, and on the right-hand side is the enclosed charge. We saw that before without writing out all the mathematics, and what this is saying is how electric fields arise from electric charges. As I've said, it's equivalent to Coulomb's law. It gives us the inverse square law. For magnetism, there's an equivalent law, but its right-hand side is zero. Its left-hand side talks about the magnetic flux, the number of magnetic field lines emerging from a closed surface, and that's zero because there's no magnetic charge. Magnetic field lines don't begin or end. Then we've got Faraday's law of induction. The left-hand side talks about if you circle around a loop, how does the electric field behave? And it says the electric field depends on changing magnetic fields, in particular, in this case, changing magnetic flux, phi b, as we've seen. The D is like the delta. It's the correct calculus thing for the delta, the rate of change. And there's that minus sign that makes Faraday's law consistent with conservation of energy, made the generator hard to turn. And finally, we have Ampere's law, which is related to the Biot-Savart law and describes the behavior of magnetic fields in a way that talks about how magnetic fields arise from their sources. On the left-hand side of Ampere's law, we've got something that talks about how magnetic field lines circle around a path around their source. On the right-hand side, magnetic or electric currents. So we have electric currents in this picture, we have electric charges in the picture, we have electric and magnetic fields, and we have those two constants, K and mu naught, the constants associated respectively with electricity and magnetism. So there's electromagnetism in math language with the English statements along beside it. Now, in the 1860s, James Clerk Maxwell, the Scottish physicist, had a brilliant insight about these equations. And I want to talk about that insight in some detail because it's really a seminal discovery in the history of science. So Maxwell's insight culminating in 1864 with his complete description of electromagnetism. Here's a picture of Maxwell. Maxwell noted that Faraday had said, look, changing magnetic fields give rise to electric fields. That's what Faraday's law says in essence. That's electromagnetic induction. We spent 2 lectures on that wonderful phenomenon. So Maxwell asked the question, could it be that changing electric fields give rise to magnetic fields? And he was motivated partly by some good physical arguments, but he was also motivated by arguments about beauty and symmetry. Nature looked kind of asymmetric if changing magnetic fields gave electric fields, but changing electric fields didn't give magnetic fields. There are also arguments associated with the Biot-Savart and Ampere laws, because they're only valid for steady currents. If you look at what happens when currents start changing, they become inconsistent with the conservation of electric charge. So there were some good physical arguments as well as this argument from sort of beauty and symmetry. So this charge conservation, inconsistent with charge conservation, really is a physical argument why you might want to have something more to these equations. So Maxwell's insight was to say, I think changing electric fields do give rise to magnetic fields. Faraday's law says changing magnetic flux, B times area, is what gives rise to electric fields. So specifically, Maxwell said, let's add a changing electric flux to Ampere's law, the same way there's a changing magnetic flux in Faraday's law. And this becomes a new source of magnetic field, just like changing magnetic flux in Faraday's law became a new source of electric field. And so Ampere's law, which originally talked about the curling aroundness of the magnetic field being related to electric currents, gets another term. Magnetic field arising from electric current, and then it also arises from changing electric flux. And in the SI system of units, the changing electric flux term has in front of it a constant which incorporates both the electric and magnetic constants together in one term for the first time. So there is Maxwell's brilliant insight. Maxwell is saying, I think there should be this additional term. At that point, he had no proof in it. Proof of this, no experimental evidence, but he could show that by adding this term, the problem with conservation of electric charge with unsteady currents went away. So there was Maxwell's insight. And here then are the complete set of equations that describe electricity and magnetism as we know it in our universe. Gauss for E talks about how electric fields arise from charges. Gauss for B says there's no magnetic charge. Faraday says electric fields arise from changing magnetic fields, and Ampere says magnetic fields arise from currents or from changing electric fields. And I want to look at the symmetries among these equations because there's a remarkable symmetry. The left-hand side of the two Gauss's laws are identical, except one's got E and one's got B. The left-hand side of Faraday's and Ampere's laws are identical, except one's got E and one's got B. And the right-hand sides are a bit different. The right-hand side of Faraday's law has a minus sign and then the changing magnetic flux. The right-hand side of Ampere's law, in addition to having the current, we'll get to that in a minute, has a positive sign and this constant, and then the changing electric flux. Well, I want to assure you that the positive sign versus the negative sign is actually a symmetry that's necessary for energy conservation, as we've seen. And the constants are purely an artifact of our unit system. In fact, there's another unit system in which I prefer to teach E&M to advanced students in which those constants are, in fact, something else, and they're the same in both those laws. But we don't need to go into that. The fact is that really, what you see there is not really an asymmetry. The important point is the right-hand sides of those laws have changing flux of the other kind of field. Now, there's also an issue with the right-hand sides of the Gauss laws in that one of them has something there and one of them has zero, and that's, of course, because there are no magnetic monopoles. If there were magnetic monopoles, there'd be a monopole charge term on the right-hand side of Gauss for magnetism, and we would actually have more symmetry. That's one of the arguments that prompts physicists to look for magnetic monopoles. Similarly, in Ampere's law, we've got this extra term saying magnetic fields arise from current, but there's no comparable term in Faraday's law. But if there were magnetic monopoles and we made a current of them, then they would also produce an electric field, and there would be a magnetic monopole current term in Faraday's law. So all those asymmetries would go away if there were magnetic monopoles. So someday if you hear magnetic monopoles have been discovered, it's kind of a nice thing for the universe, although they evidently play no practical role in the part of the universe we live in, because they're either non-existent or there are so few. So that's Maxwell's equations, but let's avoid this asymmetry associated with charge. Let's talk about what these equations look like in a region where there is no charge, in fact, where there is no matter whatsoever. So let's write Maxwell's equations in vacuum. And you might think, why do that? There's nothing in vacuum. Well, there's not nothing in vacuum. There can, in particular, be electric and magnetic fields, and Maxwell's equations in vacuum describe those fields. And so what I'm going to do is rewrite Maxwell's equations without any reference to charge. That means no reference to charge in Gauss's law, and it means no reference to current, the flow of electric charge, in Ampere's law. So let's do that. There they are again. Same equations, but simplified. Both Gauss for E and Gauss for B look the same. 0 on the right-hand side, because in vacuum there's no charge. Faraday and Ampere look the same. Left-hand side's that thing about how the fields curl around. Right-hand side's changing flux. The minus sign in one and the plus in the other are a symmetry that conserves energy, and the constants in one but not in the other are a pure artifact of the SI unit system, and so you don't need to worry about those. So now the equations are completely symmetric. In the absence of electric charge, magnetism and electricity stand on a completely equal footing in this picture. Maxwell's brilliant insight gave us this symmetry between particularly Faraday's law and Ampere's law, and now I have to introduce another brilliant insight of Maxwell's. Maxwell said, look, changing magnetic fields give rise to electric fields. That's what Faraday tells us. Changing electric fields give rise to magnetic fields. That's what Maxwell told us when he modified Ampere's law, sometimes called the Maxwell-Ampere law for that reason, or the Ampere-Maxwell law. There's a new possibility, Maxwell realizes, a kind of self-replicating electromagnetic structure propagating through empty space as each changing field gives rise to the other. Now, it's not essential that a changing magnetic field make a changing electric field, but unless the changing magnetic field is changing uniformly, and that's impossible, really, because it would just have to keep growing and growing and growing, then the electric field that gets induced is going to be changing, and it will give rise to magnetic fields that will also be changing. So this possibility of each kind of field generating the other comes up. We could look at it symbolic like this. Change in electric field gives rise to a magnetic field, which itself is likely to be changing, and the change in the magnetic field gives rise to an electric field, and that process repeats itself, that electric field changes, and we get this self-replicating structure propagating through space and carrying with it electric and magnetic fields that are continually regenerating each other. That structure is called an electromagnetic wave. So Maxwell's insight was that there would be these things called electromagnetic waves, and he was able to argue from his equations that this ought to happen, and he was able to calculate from his equations what the properties of these waves would be. And a calculus-based introductory physics course can get far enough to actually do those calculations. We won't do them here, but I will show you the results because they are profound and important. Electromagnetic waves in vacuum, it turns out, look something like this picture. The electric and magnetic fields turn out to be perpendicular to each other, and they're also perpendicular to the direction the wave is going, and that means these are transverse waves like we talked about way back in lecture 18. These are transverse waves. They're waves analogous to waves I set up on a vibrating string that were vibrating at right angles to the direction the wave was going. Electromagnetic waves in vacuum, and here you see a kind of movie of symbolic movie showing some electric and magnetic field vectors showing sort of what a wave looks like and how it propagates. And the electric and magnetic fields, notice, also are in phase. That means their peaks occur at the same point in time, and they go through zero at the same point in time. So we have electric and magnetic fields at right angles to each other and at right angles to the direction the wave is moving, and the electric and magnetic fields are in phase. How fast do these waves go? That's an important question. The wave speed is determined by Faraday's and Ampere's laws, which are making this continually self-replicating electromagnetic structure. And without going into the mathematical details, the only thing in there that could determine a speed are these constants. The magnetic constant mu naught and the electric constant K. Now let me back up a minute and talk about those constants, because they came from experiments done in the 18th and 19th centuries on simple things like static electricity and magnets and current carrying wires and the forces they produce, stuff that has nothing to do with waves. And yet, those two constants appear in these equations in a way that determines the wave speed. In fact, the constant mu naught over 4 pi k, that combination, turns out to be the 1 over the wave speed squared, and that's what the mathematics tells us that we won't work with. So the wave speed, the speed of an electromagnetic wave in vacuum, not somewhere else, is the square root of 4 pi k over mu naught, and that's important enough that we're going to do the numbers. 4 pi, 9 times 10 to the 9, Mu naught is 4 pi times 10 to the minus 7. The 4 pi's cancel. We've got the square root of 9 times 10 to the 16 when I take 10 to the 9 and divide it by tiny little 10 to the minus 7. This is all in SI units. So it's going to come out in meters per second. Take the square root of 9, you get 3. Take the square root of 16, you get 8. 3 times 10 to the 8th meters per second. Now, you may have heard that number before. It's a big, fast speed. But it's a known speed. It was a speed that had been known for a couple centuries before Maxwell's time. It is the known speed of light. And Maxwell immediately realized he had discovered what light was. He had discovered that light was an electromagnetic wave. He had suddenly brought the whole science of optics under the umbrella of electromagnetism. That is a brilliant synthesis, one of the crowning intellectual achievements in the history of science. The recognition that light is an electromagnetic wave because light travels at the speed 3 times 10 to the 8 meters per second, and indeed it can consist of these electric and magnetic fields. So let's look a bit more at electromagnetic waves, their history and their properties. So a brief history of electromagnetic waves. So we go back to Young in 1801, who did interference experiments that showed that light was a wave. Newton had believed it was a particle. Young proved Newton wrong with these experiments, that light is definitely a wave because it underwent wave interference. Maxwell in the 1860s comes along with his electromagnetic theory and shows that electromagnetic waves propagate at the speed of light and arise from his electromagnetic theory. Heinrich Hertz in 1888 tried to prove Maxwell right by creating electromagnetic waves on one side of his lab and detecting them on the other, and he succeeded. Not much later, Marconi, Italian, transmits electromagnetic waves across the Atlantic. There's actually still a Cape Cod, a Marconi monument, national monument, that in fact has the residues of some of Marconi's towers. By 1920, KDKA in Pittsburgh came on the air as the first commercial radio station in the United States. WNBT in New York came on in 1941 as commercial TV. This is a very abbreviated history. In 1947, radar had been invented during World War II, and some radar engineer noticed that his hand got warm when he put it near the radar oven, the radar antenna, and so they invented the microwave oven, which used to be a big clunking thing, just as this ancient radio and TV show. Finally, by 2000, we have cell phones absolutely everywhere. They, of course, work by electromagnetic waves, and in the 2010s and beyond, everything is wireless. Wireless means electromagnetic waves. Electromagnetic waves are not just light, but they are light. They're radio waves. They're all kinds of other waves. In fact, waves can have any amplitude, but there's a relationship between the strengths of the electric and magnetic fields, and they're related by the strength of the electric field is the speed of light times the strength of the magnetic field. Any frequency is allowed, but as for any wave, the product of frequency and wavelength is the wave speed. There's a whole spectrum of electromagnetic waves, starting with very low frequency, long wavelength waves that we use for radio and TV. As they get shorter, we call them microwaves. Then we call them infrared. As they get shorter still, then we call them visible light. There is no firm boundary. These are all the same things. They're all assemblages of electric and magnetic fields propagating through space at the speed of light. I've expanded out the visual spectrum in this from the longest wavelength, lowest frequency red light up to the violet light at the highest frequency, shortest wavelength end. Then they fade into ultraviolet, which we can't see, but cause us to be tan or cause skin cancer. They fade into X-rays, and then finally gamma rays. So there's a whole spectrum of electromagnetic waves. Where do these electromagnetic waves come from? How do we get them going? Well, you have to make changing electric and magnetic fields. And ultimately, the way you do that is by shaking an electric charge. You grab an electric charge and you shake it. You make accelerated electric charge. You've got to accelerate electric charge. Not good enough to move it at a steady speed, because then I could walk alongside it and I wouldn't see any electromagnetic waves. And Einstein would have a lot more to say about that. Electromagnetic waves come from accelerated charge. That's the source of electromagnetic waves. In radio transmitters, we have capacitors and inductors connected into a circuit. They cause electric currents to oscillate back and forth at a frequency determined by the inductance and capacitance. Sends a current up into an antenna. The oscillating charges, the accelerated charges as they move back and forth, radiate electromagnetic waves. In atomic and molecular systems, we have basically dipoles that go into oscillation, and those oscillating dipoles produce relatively short wavelength, higher frequency electromagnetic waves, typically from molecules in the infrared region of the spectrum. That's, by the way, why carbon dioxide absorbs the outgoing infrared and causes the greenhouse effect, which causes global warming, for example. Atomic systems, it tends to be more in the visible spectrum, so most visible light is being generated by atomic processes. You get to even smaller scales, X-ray tubes, for example. Electrons are accelerated by very high voltages, tens of thousands of volts. They slam into a very hard target of a material like tungsten. The very rapid deceleration produces very high-frequency, short-wavelength electromagnetic waves. X-rays, electrons spiraling in magnetic fields, as I mentioned when I talked about cyclotron motion, in the laboratory or in astrophysical situations, they produce electromagnetic waves of frequencies that depend on how rapidly they're spiraling around, and that depends on the magnetic field strength that they're spiraling in. Finally, nuclear transitions involving energy changes within the atomic nucleus, with the protons and the charges on the quarks and the protons moving around, produce electromagnetic waves of very short wavelength, very high frequency, and those are called gamma rays. But they're all the same thing. In a classical description, at least, we'll see how a quantum description alters that a little bit. They are all basically electric and magnetic fields that are self-regenerating through these processes we've talked about. So that's how we make electromagnetic waves. And characteristically, the wavelength of an electromagnetic wave is kind of related to the size of the system that's generating it. And the size of the system that responds best to electromagnetic waves is roughly the scale of the wavelength. That's why if you ever built an FM radio antenna and kind of hung it on the wall of your college dorm, it was a wire about this long, because that's about half the wavelength of a 100 million cycle per second, 100 million hertz FM radio wave. An antenna for the very low frequencies used to communicate with, say, submerged submarines, because only those waves will penetrate water. They can take up acres and be miles and miles and miles long, whereas atomic systems, very, very small, nanometers and smaller, are the systems that interact with visible light, for example. So waves interact with systems comparable to their wavelength. Well, let's talk about energy in electric and magnetic fields, and in particular in electric and electromagnetic waves. And so let's do one calculation in this final lecture on electromagnetism. Let's talk about energy in electromagnetic waves, because we've already seen from arguments involving a capacitor, which we generalized to arbitrary electric fields anywhere. We said, look, electric fields have reality and they carry energy, and the density of that energy goes as the square of the electric field, and incidentally it has in front of it the electric constant with the 4 pi there, and it has a 1/2. By the way, the 1 over 4 pi k appears so frequently it's given another name, and normally we'd see it instead of that. I just didn't want to introduce another constant. So the structure of the electric energy density is 1/2 times a constant associated with electricity times the square of the electric field. By considering a solenoid, back in lecture 38, we looked at the magnetic energy density, and we found the magnetic energy density also had a 1/2, then the magnetic constant, and then the square of the magnetic field. And again, the way the constants appear is an artifact of the SI unit system, but the important thing is they both depend on the squares of fields, and they both have the 1/2. Now, we've seen that in a vacuum electromagnetic wave, the electric field is C times the magnetic field. Well, that means the square of the electric field is C squared times the magnetic field squared. And C squared, we know, is 4 pi k over mu naught. That's where Maxwell's theory gave us the speed of the electromagnetic waves. I pointed that out when I showed how that combination appeared in Ampere's law to give us, as the only thing that could have given us a speed. So if we look at the electric energy density, we can replace E squared with C squared B squared, and then we can replace C squared with all this stuff. And so we get we get 4 pi k over mu naught. That's where the C squared was. We already had a 4 pi k downstairs here. That's going to cancel, and lo and behold, we get that expression. And there we have it. That was our expression calculated for the electric energy density. There it is for the magnetic energy density. They're equal. Electricity and magnetism stand on a completely equal footing in vacuum electromagnetic waves. The symmetry is complete. Electric and magnetic fields play exactly the same role. By the way, once you start moving through materials, that's no longer true. When light waves move through glass, for example, the interaction with the molecular dipoles in the glass actually reduces the electric field. We saw that when we put dipoles between the plates of a capacitor. And magnetic fields actually carry more of the energy in a transparent medium like glass than do electric fields. But in vacuum, they are on a completely equal footing. So that's electromagnetic fields in vacuum. They share that energy just completely equally. The symmetry is perfect and complete. Okay, well, let's wrap up by looking a little bit more at energy in electromagnetic waves. So I have shown here a little slab, a piece of an electromagnetic field. It's moving along at speed c, and I'm not going to go through the math, although it's not terribly hard. You can find very quickly that if you multiply E and B together, the strength of the electric and magnetic fields, the peak electric and magnetic fields in that wave, and divide by twice that magnetic constant, you get a quantity called S with a bar over it. That's the average rate of energy flow per unit area. It's measured in watts per square meter, and that's the energy, the rate at which this electromagnetic wave is carrying energy along. Now, this all sounds very abstract, but that is a really, really important quantity. Let me give you some values of it. In direct sunlight on Earth's surface, so you go out in noonday sun and you just put a square meter of, well, if you're at the equator, at the surface, flat, you tilt it toward the direct sunlight at some other latitude. In bright sunlight at Earth's surface, that intensity is about 1,000 watts per square meter. That means sunlight is carrying 1,000 joules every second to every square meter of Earth's surface that's oriented at right angles to the incoming sunlight, of course, under clear sky conditions. That figure is actually more like 1,400 watts per square meter above Earth's atmosphere, but there's some loss coming through the atmosphere and some reflection off particles in the atmosphere. Of course, it's much lower under clouds and things like that. But in direct sunlight, you've got about 1,000 watts coming on a square meter. That's a real number. And what is that number? It's the energy being carried in the energy of the electric and magnetic fields that make up sunlight. So when you go out and tan yourself on the beach, or when you thank photosynthesis for growing the plants that you ate, or the plants that you ate that the cow ate that you then ate, it's all coming to Earth in the form of electric and magnetic fields in these electromagnetic waves. A radio signal 5 miles from a typical radio transmitter whose power output might be 10,000 watts, it's 10 microwatts per square meter. Tiny compared with the energy density and the power in sunlight. Tiny, and yet your radio receiver is good enough to pick that up. A laser pointer has a pretty good intensity. It's about 1/10 that of sunlight. It's 100 watts per square meter. It's quite intense. You wouldn't want to look at a laser pointer, and you wouldn't want to look directly at the sun either. That can damage your eyes. The microwave intensity about 2 inches from a cell phone is not tiny. It's about 10 watts per square meter. Probably doesn't do any harm, but it's not insignificant. In fact, there's a lot of microwaves around us all the time now as everything gets more and more wireless. Starlight from a bright star is about 100 nanowatts per square meter. That's what astronomers have to work with. The laser fusion experiment at the National Ignition Facility, where they're trying to make fusion happen by bombarding a tiny pellet with 192 laser beams and making it go off as a tiny miniature nuclear explosion, is carrying about 10 to the 20 watts in every square meter. Just enormous amounts of energy being delivered there. So those are some values of energy in electromagnetic waves. Finally, where there's energy, there's momentum. And it turns out that the momentum in electromagnetic waves gets transferred to whatever the waves hit. If the waves absorb it, they get this much momentum. If they're reflected off again, they get twice as much momentum. And that radiation pressure expressed as a force per unit area is simply that intensity S divided by the speed of light. Its units are newtons per square meter. It's called radiation pressure. It's relatively weak in most situations, although in that NIF laser facility with 10 to the 20 watts per square meter, it's anything but small. It has been proposed, actually, for powering spacecraft powered by the radiation pressure of sunlight. You put a relatively lightweight spacecraft up in space and you let sunlight hit it, and the radiation pressure could be enough to accelerate it. It'd be a way of traveling without any fuel long distances in the solar system, or maybe even in interstellar space if you shine a big laser from Earth onto this spacecraft. And the picture here is the Icarus spacecraft, which was the first successful solar sailing spacecraft, and that was launched in 2010. Okay, well, let's wrap up with a look at what we've learned in this summary lecture that put all of electromagnetism together and gave us this wonderful new phenomenon of electromagnetic waves. Maxwell's equations describe fully the behavior and classical physics of electric and magnetic fields everywhere in the universe. In a vacuum, there's complete symmetry between the fields. The changing magnetic fields give rise to electric fields. The changing electric fields give rise to magnetic fields. The changing fields result in electromagnetic waves. They propagate at the known speed of light, c. They include light. They are transverse waves. There's a spectrum of all possible wavelengths and frequencies, of which visible light is only a small part. They are produced ultimately by accelerated charge, and they carry both energy and momentum.